Good. So good morning, everyone. Welcome to the Good Vibration seminars for the sixth seminar of the second season. So today we have the pleasure to have Joel Ong giving this seminar today. So Joel is currently finishing his PhD at Yale University. He's earned his Bachelor of Science in Physics at the National University of Singapore, where he studied geometric phases in curved spacetimes under the supervision of Associate Professor Kuldeep Singh. Joel is then worked under the supervision of Professor Deborah Fisher at Yale for something that is equivalent to a master's project, from what I've understood. The topic was instrumentation, and radial velocity analysis software for the extreme precision spectrograph, the Express. Then he started his actual PhD under the supervision of Professor Sarbani Basu on various topics in theoretical astroseismology. Joel should be done with his PhD next summer with a total of 6 papers in APJ as lead author. So Joel, you're welcome to share your screen. You have 35 minutes.
Okay, so before I begin, I want to say that if you want to follow along, you can find these slides on my website at this URL. Right, so thank you for the very kind introduction. So I'm going to give a rough outline of where we're going with this talk. First, I will briefly introduce the phenomenology of mixed modes for people who are not too familiar with this, if they're working on classical pulsators most of the time, for example. I will then provide some details of an analytic construction for mixed modes that Sabrani and I developed last year. And then I will go through 2 applications of this analytic construction to different problems in the astroseismology of solar-like stars, solar-like oscillations. So solar-like oscillations, as we all know, come from looking at a very narrow region of the frequency domain, where we see several peaks in a narrowly defined envelope corresponding to convectively excited oscillations like the kind we see in the sun. And these oscillations, at least in the sun, correspond to pressure waves, which yield P modes. And the dispersion relation of these pressure waves is such that they emanate isotropically from any point of excitation. So in the sun, from which we inherit much of the phenomenology, these pressure modes form a comb of more or less regular spacing, which we call the large frequency separation delta nu, with also a characteristic excitation frequency, which we call nu max, right? And it's customary to rearrange all this information into what's called an Eshell diagram by first breaking up the power spectrum into chunks of width delta nu, stacking them up above each other, and identifying ridges, each of which correspond to a different spherical harmonic degree. So for main sequence stars like the sun, these convectively excited solar-like oscillations form more or less vertical ridges on this Eshell diagram. And that's because the modes we see are all pressure waves, P modes. Unfortunately, for the majority of the stars in our observational sample are not stars like the sun. They are much more evolved, and this is because both the photometric amplitudes and characteristic excitation timescales of these oscillations increase with luminosity, which in turn increases with evolution. And you can see from these plots of the observational selection functions for the Kepler and TISS samples that the majority of the stars for which we have detected solar-like oscillations tend to be at the high luminosity end of the observational phase space. So what's problematic about this in terms of using phenomenology inherited from the sun is that the observational morphology of the oscillations we see in these evolved stars is different from that in the sun. So if we follow the evolution of a star off the main sequence across the Hertzsprung gap and up the red giant branch, the Eshell diagrams show phenomenology that is very different from what we see in the main sequence stars, because these otherwise vertical ridges are interrupted by the introduction of a bunch of extraneous modes. And the interaction between these extraneous modes and the otherwise vertical QRP modes becomes increasingly rapid and complicated as we evolve, as we cross the X-plane gap and evolve. Right? And at some point, we transition from being mostly P-dominated to having intermediate fractions of P-mix and G-mix modes to being dominated by G-mix modes. So in the main sequence stars, the Emission diagrams look very similar to that which we see in the Sun. They're dominated by P modes. As we cross the X-plane gap, we have modes of very intermediate character in between the pure P modes, doing really complicated things. And then once we are on the red giant branch, the majority of the modes we see do not behave like the P modes at all, except for a few that lie where the nominal P nodes are supposed to be, which in this case, these are the dipole modes, and they take on larger amplitudes there. So if we were to unwrap the earlier animation such that time is now on the horizontal axis of the plot, we would see that the evolution of these mode frequencies goes from left to right. This is because I've normalized these quantities such that the pure P modes, which I show here with the orange dashed lines, also evolve horizontally from left to right. And the reason they do this is because the frequencies of these pure P modes are proportional to delta nu multiplied by some things that don't really change over the course of evolution very much, right? But the actual mode frequencies of these stellar models, which I show with the blue curves, only follow the evolution of the pure P modes some of the time. And the places where they do not follow the evolution of the pure P modes also appear to evolve smoothly over time, which I show here with the green lines. These correspond to the frequencies of G modes. And the propagation of these G modes is governed by a slightly different dispersion relation, which tends to favor propagation of the waves in mostly the lateral direction, not the vertical direction. So the frequencies of these G modes are specified by a different asymptotic relation from those of the P modes. In particular, it is the periods and not the frequencies that are proportional to some characteristic spacing. Now, if we were to look more closely at this diagram, we will find that the actual frequencies of oscillation, again with the blue curves, interweave between these two families of P modes and G modes in such a way that they exchange character as they go from one to the other, and they evolve in such a manner as to avoid where the two families of modes cross. And this is why this kind of phenomenon is called avoided crossings. Avoided crossings appear in many areas of physics, and we will return to this shortly. Now, if you want to get a better handle of what causes this kind of mode mixing, it is instructive to take a look at models of the structures of these evolved stars. So working through the theory of this, we know from countless lectures in university that the propagation of waves in these self-gravitating objects is governed by two characteristic frequency scales for non-radial modes of oscillation. Right? We have the Brunt-Weisela frequency, which I show here with the orange curve, and the Lamb frequency, which I show here with the blue dashed curve. And these govern the kinds of oscillations that you are allowed to have for a mode of a fixed frequency. So for a horizontal line on this diagram. In particular, if the frequency of the normal mode is higher than both the Lamb frequency and the Brunt-Weisela frequency, then the dispersion relation is that of a pressure wave with isotropic propagation. And conversely, if the frequency of the mode is lower than both the Brunt-Weisela frequency and the Lamb frequency, then we have gravity modes with mostly horizontal propagation. Now, the thing is that for some stars, like the stellar structure used in this diagram, I show here the characteristic excitation frequency Vmax with the horizontal dotted line. And we see that both of these conditions are satisfied in different parts of the star. And so the actual normal modes that are supported by the stellar structure have mixed character. They behave like P modes in the outside bits of the star and like G modes in the inside bits of the star. If you were to attempt to find some kind of eigenvalue equation for these mixed modes, similar to the asymptotic relations we had for the pure P and the pure G modes, so far the most reliable or most commonly known at least approach relies on what's called a local asymptotic analysis, or the JWKB approximation. The problem with this, that there are two main problems with this. The first problem is that the assumptions going into the JWKB approximation aren't always satisfied by the stars that we tend to observe with Kepler tests, right? The most important approximation going into the JWKB analysis is that the wavelengths corresponding to this dispersion relation should be much smaller than any length scale associated with the stellar structure. And you can see for this particular stellar model, that's not true. The wavelength of the interior G mode for this particular mode in a subgiant is comparable to the size of the G mode cavity itself. And in such circumstances, JWKB analysis is not supposed to work. The second problem with such asymptotic analysis is that operationalizing this theory is pretty difficult from an observational perspective. So we tend to operationalize this construction by way of a mixing function zeta, for example. But different definitions of zeta, some from the mode frequencies themselves only, and some relying on access to the internal stellar structure, don't necessarily agree, as I show on this diagram. They agree on the broad aspects of things, but in detail, they might not agree sufficiently enough for a quantitative comparison. So an alternative approach that doesn't satisfy from all of the shortcomings in the asymptotic analysis is to approximate these mode frequencies with ideas from classical mechanics. In particular, if you treat each normal mode as being described with some mass and some restoring force, you can find the eigenvalues of the combined system you can find the normal mode frequencies of the combined system by looking for the eigenvalues of some matrix, in this case, that happens to be diagonal in classical mechanics. And all you've done so far is make a simple problem difficult for yourself. But you can make the configuration itself more complicated by adding additional springs connecting different masses in the system. And when you do this, you can again find the normal modes of oscillation with exactly the same procedure. You find the eigenvalues of this large coupling matrix now with off-diagonal elements, right? And running through this procedure gives you eigenvalues of these matrices that resemble the phenomenology we see in the avoided crossings in astroseismology. The main problem with this approach, however, is that until very recently, that is until us, there was not a well-defined procedure to find the elements of this matrix and associate them with quantities in the stellar structure in a well-defined way without the introduction of additional free parameters or doctoring the stellar model in some fashion. Right? And so this renders this approach not particularly usable for evolved stars where you have many-to-many mode coupling, that is many P modes coupling to many G modes, using complicated configurations of avoided crossings. So to address both of these shortcomings, Sabrani and I proposed a different and also non-asymptotic analytic formulation. And the guiding intuition behind this new approach is that we steal ideas from quantum mechanics rather than classical mechanics. So the main idea is that in quantum mechanics, we can have complicated systems like molecules, but we also know a priori that these molecules are made of simple things, atoms, right? So I will walk you through the procedure for how this works for, say, the hydrogen molecule. The hydrogen molecule, as we all know, is made of 2 hydrogen atoms. And the hydrogen atom, you can study in some detail in your second year of undergraduate physics or something, right? So if you want to get a handle on the eigenstates and eigenenergies of the hydrogen molecule, you first understand the hydrogen atom very well, and then you think about what you have if you have two hydrogen atoms. If the hydrogen atoms are at an infinite separation, then you already know the eigenstates and eigenenergies of the combined system. They're just two copies of the eigenstates and eigenenergies of the hydrogen atom, localized at either atom 1 or atom 2. As you bring the two atoms together, reducing the interatomic separation, in some cases, you can approximate the Hamiltonian of the combined system quite well as the Hamiltonian of atom 1 plus a small perturbation from atom 2, or vice versa, the Hamiltonian of atom 2 plus the Hamiltonian plus a small perturbation from atom 1. If this approximation is good, that is to say, if the coupling between the two systems is sufficiently weak, then we can approximate the eigenstates and eigenenergies of the molecule as being linear combinations of the eigenstates of the atoms, either constructively interfering, in this case, to give you the ground state of the hydrogen molecule, or destructively interfering to give you, in this case, the first excited state of the hydrogen molecule. Now, in general, you don't just have, two states talking to each other. Each of the atoms has usually a well-defined family of eigenstates, and likewise, the eigenstates of the molecule must be combinations of essentially all of the eigenstates of the atoms considered separately. So to find the coefficients of these linear combinations, we solve what's called a generalized emission eigenvalue problem, where the matrix elements of this eigenvalue problem are found by taking overlap integrals of either the Hamiltonian or the identity operator with respect to the eigenfunctions of the isolated atoms, right? And then the eigenvectors that emerge from this eigenvalue problem are the coefficients of these linear combinations, and we also get the eigenenergies associated with these linear combinations. So the situation in astroseismology is then entirely analogous. In astroseismology, associated with a stellar structure, we have a wave operator yielding modes of mixed character. The hard part here is figuring out a way to decompose such a wave operator into either a pure G-like wave operator with a small remainder term for the p-mode cavity, or a pure P-like wave operator with a different remainder term for the G-mode cavity. So such a decomposition was proposed by Eisenman et al. 1977, who referred to this kind of thing as pi modes and gamma modes, but they didn't get it quite in a way that is usable for these evolved stars. And so Sabrani and I found one decomposition of the wave operator that happens to work for mixed modes in these evolved stars. And once we have the eigenfrequencies and eigenfunctions of the isolated P and G modes, then we can turn the crank on exactly the same matrix machinery as used in quantum chemistry, right? We express the mixed mode wave functions as linear combinations of the wave functions of the pure P modes and the pure G modes. And we find these linear combinations and the associated mixed mode frequencies by solving exactly the same kind of generalized emission eigenvalue problem, where the matrix elements now are overlap integrals between the isolated P mode and G mode wave functions with respect to either the wave operator itself or the identity operator on the right-hand side. So the details of this are in our 2020 paper, and a numerical implementation of this is now available in Jaya version 6. So this offers some, quite satisfying theoretical resolutions to earlier open problems. In particular, as I said before, operationalizing the asymptotic construction requires the construction of a different quantity called the mixing function, which is often referred to as zeta, and it's not a priori obvious what this function zeta corresponds to. So we find that we are able to construct a quantity that is basically the norm of the gamma mode component of these linear combinations that more or less reproduces exactly what zeta is supposed to be. And in turn, this, in a quite satisfying fashion, this tells us that if we wanted to generalize what zeta is to where the asymptotic approximation cannot hold, we have a natural way of doing this for essentially mixed modes in all stars, not just red giants where we can get away with using the asymptotic approximation. The other thing this tells us is that if you look at the eigenvalue equation here, we have not one, but two matrices. And so that tells us that we have not one, but two different kinds of coupling strength in the problem. And that And I show here the coupling matrices associated with a subgiant model. These are block matrices, so this is a diagonal, more or less diagonal matrix for the P mode cavity, for the G mode cavity, and we have cross terms on both the left-hand side and right-hand side of the eigenvalue equation. And you can see that these coupling strings actually are quite complicated functions of frequency, and they don't necessarily behave in the same way. So the flip side of this is that the use of the asymptotic approximation may not give us sufficient degrees of freedom to correctly describe mode coupling in these evolved stars. Okay, so I will now walk through, like as promised, two applications of this construction, two different problems in astroseismology. The first is primarily methodological, right? It's to do with the surface term and how it interacts with mixed modes in these evolved stars. So to recap, for those who are not familiar with the problem, for stars, like for the sun in particular, we are able to match the interior structure of the sun in standard solar models. So here I show the relative discrepancy between between two standard solar models and the sun for the sound speed and density as a function of radius. And we can see that the numbers on the vertical axis are quite small, which indicates that both of these standard solar models reproduce the interior structure of the sun quite well. However, if you were to compute the frequencies of these standard solar models, you will find that they don't agree with that of the sun, with those seen in the sun. And the discrepancy between the frequencies of the models and the observed frequencies of the sun appear to be a systematic and smooth function of frequency. And if we were in turn to use these uncorrected frequencies to constrain the properties of the sun, using the same methods as we normally use in astroseismology or solar-like stars, we would actually get the mass of the sun wrong by about up to perhaps more than 5%. So in practice, when we use mode frequencies, not just for the sun, but generally for sun-like main sequence stars, to constrain the properties of stars, we have to first subtract away a smooth function of frequency, the astroseismic surface term, before matching the observed and model frequencies together to find a likelihood function. And the problem with this is that the interaction between the surface term, these surface term corrections, and mixed mode coupling is not immediately obvious, right? Because if we think about the problem a bit more deeply, let's say that we have two stellar structures with identical global properties, but with only differing structures in the near surface layers. And we do this because we know that the surface term arises from modeling errors in how we treat 1D convection and magnetic field and so forth that are mostly confined to the near surface layers. What we can do is that we can interpolate between these two structures, going from one to the other, with a small quantity lambda, where lambda goes from 0 to 1. And the difference between the two structures gives us a perturbation operator that is localized to the near surface layers, right? Now, since this perturbation operator is localized to the near surface layers, its action on the pure G modes must be very small because the G modes are confined to the stellar interior. And so if you were to think about how the mode frequencies will respond to such a perturbation, the P modes will feel the full force of the surface term. And so the deviation between the P mode frequencies between the model and the observed star must more or less satisfy the same kind of smooth function of frequency that we saw in the sun. However, the action of the surface term on the G modes must also vanish, right? And it is therefore traditional, I would say, to apply some kind of fractional correction to the mode frequencies, depending on whether the mode is P dominated or G dominated. And again, the fraction of the correction that is to be applied to the mode frequency is parameterized traditionally by the same kind of mixing function zeta that we saw earlier. However, we can see on this diagram actually that there are two operations involved in correcting for the surface term, right? The actual surface term acts on the P modes, which then give mixed mode frequencies under the operation of mode coupling. right? Whereas the traditional approach to correcting for the surface term essentially begins with mixed mode frequencies of the model and then applies some weighted fractional correction to the mixed mode frequencies alone. Now, unfortunately, mode coupling is a nonlinear operation because it involves solving a high order polynomial to get a high order characteristic equation associated with the coupling matrices. And so these two operations don't necessarily commute. And when they don't commute, then you may potentially commit some kind of systematic error. So I will demonstrate with an animation how the traditional approximation to mode coupling may fail. What I show here are the mixed mode frequencies associated with a red giant stellar model, right? And in the background with the gray points and gray dashed line, I showed the frequencies of the underlying pi modes associated with the same stellar model. What I will do is I will slowly turn on perturbation to the surface of the model, and we will see how the actual mode frequencies of the model respond to this perturbation, as well as what the traditional approximation to mode coupling will predict for how the mode frequencies will respond to this perturbation. So here we go. Right, so you can see several things going on. The first is that, I will play this again. The first is that different G modes come into and out of resonance with the underlying P modes as the surface localized perturbation is turned on. The other thing we can see is that the traditional approximation to mode coupling does not yield the same results as when the mode coupling is fully accounted for in the surface term calculations. So a different way of looking at the same thing is, again, with respect to the mixing function zeta, right? So I show in this diagram the mixing function zeta as a function of frequency for some modes in the neighborhood of pi mode. And the pi mode frequency is itself shown with the vertical dashed line. So here we go. So as I said earlier, the traditional approach to mode coupling applies a fractional correction to every mode depending on the value of zeta. So if zeta is 0, it will apply a full correction to the mode. And if zeta is 1, it will apply no correction, right? But it doesn't actually change zeta itself for any given mode because it doesn't know how to do that, right? Whereas if we were to fully account for mode coupling, what happens is that the pi modes evolve essentially independently of the gamma modes as we turn on the surface localized perturbation. And then the frequencies of the mixed modes are only computed after the surface term correction is applied. So if we were to, again, unwrap this animation such that time lies on the horizontal axis, what we see is a hidden family of avoided crossings in phase space. As the surface term surface localized perturbation is turned on, lambda going from 0 to 1, we find that the P mode, the underlying pi mode, responds in a linear fashion to the action of this surface localized perturbation. But the actual mixed mode frequencies undergo a series of avoided crossings following that of the pi mode. And we can see now why the traditional approximation to mode coupling might fail. The traditional approximation of mode coupling yields corrections that are proportional to the strength of the surface localized perturbation. And so it can only ever give you straight lines. It is a first order approximation to mode coupling. And these straight lines are tangent to the blue curves at lambda 0, where the surface term is weak, right? So the problem then is that if you have a stellar model that is sufficiently far away from the actual properties, the actual properties of the star, the fake surface term that you need to impart to this stellar model in order to match the observed frequencies is sufficiently large that the first order to approach to mode coupling might fail. So that is it for the forward problem. That is, what happens to the mode frequencies when you apply a perturbation to the surface. But we are also concerned with the inverse problem, right? What happens to the properties of the stars that you measure if you don't fully account for mode coupling when using this, when applying a surface term correction and computing a likelihood function? So here I show a comparison between the stellar masses that we would obtain from grid-based modeling of subgiant stars in the Kepler field. On the horizontal axis, I show the masses obtained from the first order approach to mode coupling, that is the orange lines in the previous diagrams. And on the vertical axis, I show the masses obtained when mode coupling is fully accounted for. With the different colors, I show the results of grid-based modeling with respect to two different constructions of the surface term. One is an explicit parametrization from Bollinger's on 2014, and the other is the non-parametric epsilon matching algorithm of Roxburgh 2016. And we find that the trends are broadly speaking the same. Right. Most of the points of both colors lie above the line of equality, shown here with the dotted gray line. And this implies that the first order approximation to mode coupling yields systematically lower stellar masses compared to when mode coupling is fully accounted for in this grid-based modeling exercise. If we look in more detail at this pair of points, they are the same star, just with different corrections for the surface term. This star happens to be TOI 197, which has been characterized also in exhaustive detail because it was one of the test astroseismology first light papers. So we can have a look at the results of grid-based modeling and compare them to the reference values from Huber et al. 2019. And we see that the first order approach to mode coupling, with and without the introduction of luminosity as an additional spectroscopic constraint, shown with the blue contours and the gray contours, differ systematically from when mode coupling is fully accounted for in the likelihood function, shown here with the orange and black contours and histograms. In particular, we see that when mode coupling is fully accounted for, the introduction of luminosity as an additional constraint significantly tightens the posterior distribution associated with these stellar parameters, indicating that they are in agreement, and adding luminosity just tightens our constraints. Whereas for the first order construction to mode coupling, we see that adding the luminosity as an additional constraint to the seismic information doesn't do very much, and in some cases completely changes the answer, which indicates that the luminosity constraint may potentially be in tension with the seismic constraint. So this tells us that if you want to get subgiants right when applying a surface term correction, you kind of need to account for mode coupling fully. And if you don't, then you may incur both single target measurement error and population-wide systematic errors. The next application of this mode coupling construction is to slow rotation in evolved stars. I know I'm running out of time, so I'll try to speed up. So we know that the introduction of slow rotation into stars breaks spherical symmetry, and now we need 3 rather than 2 quantum numbers to describe any given mode, right? And for slow rotators, the amount of splitting from a single mode into a multiplet component is given by an integral of some kernel function over the entire stellar structure. So for pure P modes, the sensitivity of these kernel function is quite evenly distributed throughout the entire stellar structure. But mixed modes are combinations of P and G modes. And while the pure pi modes in these mixed mode stars behave like the P modes we see in the sun, the sensitivity of the mixed modes is mostly localized to the stellar interior. And so at the same time, we also know that these stars must have their cores spin up and envelopes slow down as they evolve up the radiogiant branch. And so we can use these mixed modes to probe internal radial differential rotation. So the picture here is that the pure P modes are supposed to have a much smaller amount of rotational splitting from the pure G modes, right? So here I show the P mode frequencies with the dashed lines, the G mode frequencies with the dotted lines, and the different values of M in every multiplet component with different colors. When we introduce coupling between the P and G modes, we find that each color, that is to say, each value of the azimuthal order M, exhibits an independent family of avoided crossings. So you can see here that the orange lines and curves form one avoided crossing here and here. The blue lines and curves form one avoided crossing here and here, and they don't really care about what each other are doing. This is true to first order in the rotational rate. And this is surprising because this is first order analysis. Everything is proportional to omega, but it's giving you curves, right? These curves are not straight lines. In practice, we also are not able to identify in advance what the azimuthal orders of these modes are. So if you were to see a star at this particular value of the rotational rate, for example, you might have a look at these three modes and think they were a rotational multiplet because they're so close together, and you would be wrong. So there's two things going on here. First, these avoided crossings generate asymmetries into the rotational multiplets, even when there isn't supposed to be any from magnetic fields or whatever. And second, we might get the mode identification wrong and incorrectly diagnose asymmetric splitting. Sorry, I really am running out of time, so I'll have to speed through these slides. Yeah, when we are really far up the red giant branch. Okay. Yeah, when we are really far up the red giant branch, right? We measure actually asymmetric splitting. That's to say, the asymmetries in the rotational multiplets that we will obtain are comparable to those that would be produced by magnetic fields buried in the core from Lisa Brugnaic's paper. And this means that if you were to take the asymmetries that you measure in these mixed mode multiplets at face value, you would incorrectly diagnose the presence of magnetic fields either in the core or elsewhere, right? And so the conclusion we draw from this is that these avoided crossings must be accounted for fully to make credible statements about other sources of potential asymmetry in the rotational splitting, such as magnetic fields. Okay, so to summarize, right? First, we have described an analytic construction of how to decouple the P and G components of the wave operator in these involved stars to give you pure P and G modes, and then how to recouple them to give mixed modes in a semi-analytic fashion. Then we have described the implications of this construction for an open methodological problem, that is the surface term correction in mixed mode oscillators. And finally, we have studied some implications of this new construction for the study of rotational splitting in evolved stars. Okay, so that's all for my presentation. I will stop here and take questions. Thank you for your attention.
Thank you very much, Joel. You're right in time. So I'm sure that we will have many questions. I encourage our younger colleagues to dare ask some. And now I see Thierry raising his hand. Okay, Dennis Stella was the first one. So Dennis, go ahead.
Yeah, hi, well, thanks for a great talk. So 2 questions. You said that Java version 6 implement this. Does that mean that you can get Java to output the pi and gamma modes?
Yes. So these are the options I implemented in Java. And Rich Townsend was very kind. He was very nice about telling me how to format things in a way that plays nice with the existing stuff in Java. So yes, there are now parameters in Java that you can set to get pure P and pure G modes out of a given stellar model.
The other question is, apart from for the last part you talked about, where it sounds to me that rather than having a red giant, you have specific modes that have, their intrinsic flavor of G and P and for particular, say, rotational kernels. You can split them up kernels you want. Is that correct?
Yes. So let's see. This is actually what I've been working on for my postdoc applications, right? You can see that even the most P-dominated mixed modes are sensitive to co-rotation in some kind, right? And the rotational kernel for the P-dominated mixed modes do have a non-trivial contribution from the core. But with this construction, we are able to now construct pure G-mode rotational kernels and pure P-mode rotational kernels. And the hope is that I will be able to use this to perform rotational inversions in only the envelope without contamination from the core.
Okay.
Excellent. So I think that Thierry Borchot was the next one to raise his hand.
Yeah, hi Joel. Thanks for a very nice talk. I will come from the pragmatic side. How would I implement your approach into identifying the L1 mixed mode in the future star that we'll be observing with Plato, say? I mean, you know the kind of work I've been doing recently.
Okay, so I've actually been working on this with Guy and Martin to implement this in PBGEM. So the idea is that PBGEM uses what I call generative models, right? The idea with PBGEM right now is that you first begin with a guess for delta nu and so forth. And then based on these guesses, you generate the full list of modes that you would expect to see. And then you vary delta nu, epsilon, and so forth until this matches until a generated power spectrum matches the actual power spectrum to within some tolerances. The problem is that we don't have an asymptotic relation for these mixed modes, of course. But what we can do is that we can generate pure P modes and pure G modes with their own asymptotic relation. And then we can learn priors on how these mode coupling strengths, for both matrices, change as a function of delta nu and epsilon and so forth. And we can then generate mixed mode frequencies by solving the appropriate matrix coupling equations. So that's what we have been working on for the extension to PBGEM, which we're calling Reggae for now. So, I imagine, sorry?
Yes, sorry. Then would it be possible to have kind of a description of the coupling factor as a function of frequency or something like that, so that we could shy away from the constant Q factor that we have?
Yes, exactly. So the other advantage of this construction is that we can actually write down closed form analytic expressions for what the off-diagonal coupling terms are supposed to be. And based on this, we can extract the first order frequency dependence of what these coupling terms are like. So if for a fixed n of g, for example, we can say with some certainty that the pi gamma remainder term is proportional to is proportional to omega of g squared, for example, right? And so, and likewise on the right-hand side, we are able to say that the off-diagonal terms are proportional to the ratio of omega p to omega g. And when you put things into that kind of coordinate system, you actually significantly reduce the number of free parameters you need to describe the frequency dependence. So that's what we've been working on for Reggae 2.
Okay, thanks.
Okay, I think that Benoit was the next one. Benoit?
Yeah, hello everyone. Thanks, Joel, for your presentation. I have a question about the asymmetrical rotational splitting.
Yes, I was hoping you would.
Yes, since we show in a paper 3 years ago that in fact asymptotic development is able to compute asymmetrical splittings, and in fact they agree so good, so precisely with what is observed that in fact at which level do you expect your theory to be precise in order to test additional elements as magnetic fields you mentioned in a study with Lisa Bunier?
Yes. So the primary caveat to this is that it's true that the asymptotic construction is able to describe asymmetric rotational splitting, but this is only true in the case where the rotational splitting in the P modes is negligible, right? So I've shown here the zeta function, the mixed mode coupling function, as a function of frequency for 3 different multiplet components. So they're colored by different values of m. Right? And I've joined the different modes with the same value of m with the same color. I also show the location of the notional pi modes underlying this rotational multiplet with the vertical dashed lines. And finally, I've joined up all the modes with dotted lines. So in cases where you are able to discern some rotational splitting in the pi modes, what you will find is that if you tried to construct a single mixing function zeta out of all the available modes, that mixing function will have a very complicated structure. You can see here that the dotted line describes a function with 3 local minima rather than 1 local minimum as would be expected from the coupling function, generally speaking. And this is because in these cases, you actually have 3 different mixing functions zeta, 1 for each multiplet component M. This is not a problem if you do not have rotational splitting in the P modes, but if you want to diagnose rotational splitting in the P modes in the first place, your model needs to be sufficiently flexible to allow this.
Yep.
I hope I answered your question.
Not sure, but certainly it's not here the place to discuss in detail such point.
Okay.
Thanks a lot, Joel. Your work is great.
So, Saskia, you had a question also?
Yes, thank you very much. Thank you very much, Joel, for a very interesting talk. I just wanted to come back to the answer you gave to Dennis, where you in the future want to see if you can actually get the rotation for the envelope separate from the core rotation. Yeah. I just wanted to flag that one of my students, Felix Alborn, has just submitted a paper where he is essentially doing a similar thing from a very different approach. So he has changed a little bit the objective function in the molar inversions, and he comes also to the conclusion that you can actually suppress the core rotation and only get the envelope rotation. And I think it would be very interesting when you have developed your method that you can also maybe compare the results and see if there are differences or if you come to the same place. I think it's very interesting.
I agree.
Different ways you can do this.
Yeah, I agree. I think there are very good reasons to be doing this, in particular because envelope differential rotation is a strong prediction of many different theories of angular momentum transport. And so it's imperative that it be constrained. Yeah.
Yes.
Charlie, I think you had a question.
Yes. Thank you, Joel, and hello, everybody. I just 2 questions. The first one is when you're building your mode coupling theory, I didn't understand if you use a perturbative approach or not, because you separate both gamma and P operators, and then when you solve the system, do you use a perturbative approach? Or?
No, we do not.
Okay.
The caveat is that the accuracy of the, so I should specify that that these linear combinations of pi and gamma modes are only good descriptions of the mixed mode wave functions when the coupling between the P and G mode cavities that is given by the overlap integrals is sufficiently weak. We find numerically that it is weak even in the case of the strongest mode coupling for subgiants. So this is a good approximation. But that is a limitation inherited from the construction in quantum chemistry, where again, you can only really use the linear combinations of atomic orbitals to get molecular orbitals when each atom can be treated as a perturbation to every other atom.
Yeah, okay. But yeah, I believe that in subgiants, the coupling factor could be very high, so the coupling quite high.
Yes, it is,
so
but it's still sufficiently small.
Okay. And the other question, maybe it's more a comment, I don't know. When you solve this system, you have different parameters. But
no, there are no free parameters in this model.
Yeah, okay. But
everything
I mean,
here is specified by, sorry.
For example, the frequency here, you have to compute the frequency omega squared omega.
Yes.
You have to compute it from numerical. You solve the wave equation for the P and the gamma modes. If I well understood.
So So what we do is that when we solve the system numerically, we solve numerically for the frequencies of the P and G modes, as well as their wave functions. And then everything else follows as overlap integrals. So this actually makes it more computationally expensive than the asymptotic construction. And the primary limitation is that the size of the matrices also grows as you go up the red giant branch. And matrix factorization goes as O n cubed. So beyond a certain point, this is no longer computationally feasible.
Yes, so what is the advantage compared to numerical, to compute the mixed mode frequency directly from a numerical, what is the advantage?
Okay. So that we have two advantages. First, it is of course applicable to when we need to apply operations out of order, like when we are applying these surface term corrections, we must have access to the pi mode system and must have access to the mode coupling. Otherwise, we're not able to apply any kind of correction, because if you apply the correction to fractional correction to the mixed modes, you will get things wrong, right? The second,
so you are talking about Bolin-Gison corrections?
Yes.
So actually, the factor 1 over the inertia.
Yes. Yes. Here.
Okay.
Yeah. Okay. So if you apply this kind of correction, you are basically applying a non-linear operation, that is a mode coupling, implicitly, right? Because that is done automatically when you solve the wave equation anyway. And then you are applying a linear operation, that is the partial correction for the surface term, weighted by the inertia ratios. Whereas what you need to do is the linear operation first, right? That's the surface term correction. And then the mode coupling, which is nonlinear. And when they do not commute, is where things break down.
But if you take the mode, sorry, just one last question. If you take the mode inertia from the full numerical computation of mixed mode frequencies, so it's still wrong, because you were talking about first using the first order mode coupling and the full mode coupling. But if you compute the frequency from full numerical computations with gyre, for example, you have the full mode coupling also inside. So
yes. But what I'm saying is that when you apply the Bolin-Gison correction in particular, for example, to the mixed mode frequencies, right? The problem is that for red giants, you will never get a mode with zeta of 0. And so you will never, ever apply the full weight of the correction to any of the modes. But the response of the mixed mode frequencies is such that there is a P mode for which the full correction has been applied that is then coupling to a different set of G modes that have come into resonance with it. And so you will have a P-like mode where the full correction is applied, which you cannot ever get with the naive Bolin-Gison correction. You must use the coupling matrices in this case.
Okay. Okay, thanks.
So thank you very much, Joel, for extensive answers. So I think we will thank again Joel for a very interesting talk about a lot of work which has been done during his PhD. I just have a couple of announcements now regarding the Good Vibration seminars. So next occurrence of the seminar will be in 2 weeks, and it will be given by Gabor Kovac from Konkoly Observatory in Hungary, and it will be about numerical modeling of stellar pulsations in 2D and 3D. And also another announcement, so we will have an open call of applications for the Good Vibration seminar of next semester. So please send it around. We will send it around next week, most likely. Please circulate it and encourage your students who are towards the end of their PhD to apply. So thank you everyone for joining again, and thank you, Joel, for a very, very good talk.
Thank you for having me.
See you all in 2 weeks. And maybe the people from the steering committee can stay connected. Thank you.